Will be a video demonstration of at-risk in doing Monte Carlo simulation in Microsoft Excel. This is specifically made for SE385 decision analysis at the United States Military Academy. So in this scenario, we're going to be looking at automation. So we're comparing two different processes for building a ground robot. Each process consists of 3 steps: hardware fabrication, software coding, and integration. You have a customer lined up who's willing to buy all the robots that you're able to produce in 2 weeks, where those 2 weeks consist of 80 hours. You'll profit $500 per robot. So with that in mind, you have 2 processes in place that you can use. The first process is the way that you currently build your robots. Each of the 3 processes have uniform distributions. The hardware fabrication is 8 minutes plus or minus 2 minutes. The software coding is 6 plus or minus 2 minutes. And the integration is going to be 20 plus or minus 6 minutes. You're also looking at a process that's more automated, but will cost $5,000 in new machinery. This distribution tends to follow a normal distribution rather than uniform distributions. It has a pretty low standard deviation because it is automated. So for hardware, you have a normal distribution with a mean of 8 minutes and a standard deviation of 1 minute. Software, you have a normal distribution with a mean of 6 minutes, standard deviation of 1 minute. And for integration, you have a mean of 20 minutes with a standard deviation of 3 minutes. First thing that we're going to do is we're going to use a Monte Carlo simulation to identify the number of robots that can be built in 80 hours with each process. This is going to be using the at-risk software in Microsoft Excel. So first thing that you're going to do is you're going to load Microsoft Excel and load at-risk. We'll now build out the Monte Carlo simulation for the 2 different processes for constructing the ground robot. You'll notice that I have at-risk loaded, Microsoft Excel loaded. I also took a screenshot of the scenario so that the numbers are readily available to me. So let's start building. I'm going to hardware fabrication, software coding, integration, and I'm going to call this process 1, process 2. All right, process 1, we can now define the inputs. We know that for hardware, it's a uniform distribution with plus or minus 2. So I'm going to define it as a distribution. So you'll see right here that I have normal and uniform that pop up immediately. That's just because I use these 2 the most frequently. So it's under recently used. If I don't have it there and you don't see it, just go to all, scroll down, uniform, select distribution. So it's 8 plus or minus 2, so it's going to be 6 to 10. Hit OK. Now I'm going to do the same thing again, another uniform distribution for software coding, and this is going to be 4 to 8. And again for integration, this is going to be a uniform distribution from 14 to 26. I'm going to hit OK. So that's process 1. Process 2 is going to have normal distributions. So distribution, scroll up, normal, it has a mean of 8 with a standard deviation of 1. Distribution, normal distribution, 6, 1. And a normal distribution of 20 plus or minus, with standard deviation of 3. I'm going to hit OK. And so now the total development time is going to be the sum of these times. It should be the same for both of these, just because it's showing the average values. Just going to center these so it looks a little nicer. And this is in minutes. Actually, all of these are in minutes. So now the total number of robots built is going to be 80 hours times 60 minutes divided by that time. So 141.176. And I get something similar for that side. And because it's a you can't have a fraction of a robot. I'm just going to go with round, and I'm just going to round that, set to 0, and do the same here. So now we have 141 robots that are built over the 80 hours using the two processes. And because the mean times are the same, because the mean times are the same, we would expect the same things. However, because there's distributions, it would actually be different. So what I'm going to do now is I'm going to define the total number of robots for process 1 as an output. I'm going to call this total number of robots process 1. And I'm going to define total number of robots for process 2 as an output as well. I'm going to hit OK. I'm going to set for 1,000 simulations, and I am going to hit simulate. And it ran pretty fast. And it creates a probability density function. And because it's whole numbers only is showing it's discrete. But I can make this a cumulative ascending, so that's more like what we see as a cumulative risk profile. I can also have an overlay. So if I click on overlay, add overlay, and I can add process 2 on as well. And we can see that process 2 has a higher number of robots for a certain percentage of the time, and has less robots for a certain percent of the time. So if we look at where that crossover point is, it's right around 50%. So and that's what we'd expect with a normal distribution. So about 50% of the time, process 2 is able to build more robots. And about 50% of the time, process 1, the standard way, is able to build more robots. What we're going to do is we're going to use precision tree to determine whether or not to pay for the automation based on the outcome of the stochastic model. So we're going to use the outputs from our at-risk software with precision tree. So we're now going to build a decision tree using precision tree. So you can see that precision tree already open, and I'm going to just go ahead and build it right on the same spreadsheet. So I'm going to close the at-risk output window, and I'm going to hit decision tree. Start right there. New tree, and we're going to call it lit by automation. By automation. All right, and so I'm going to start out. I have a decision 1. Go with your status quo or automate. If I automate, we know it's going to cost me $5,000. So if I go with the status quo, now there's going to be a distribution of outputs. If I'm using the extensins once in McGill method, I'm going to be concerned about the 10th, 50th, and 90th percentile, and I'm going to model that accordingly. So I'm going to create a chance node here, have 3 branches. Branch 1, I'm going to call 10th percentile, 50th percentile, 90th percentile. The probabilities are going to be 16.7, 66.6, 16.7. I'm going to copy that subtree for the bottom as well. So I currently don't have values in here. So with the status quo, I'm looking at process 1. So in that case, I can actually put in what the 10th percentile is. It's going to be, I can use equals risk percentile. And I'm going to highlight the total number of robots. 10th percentile, so 0.1. And I'm going to multiply that by $500 because our profit is $500 per robot. I'm going to hit enter. So I'm going to copy and paste that for the other 2 and change it to 50th percentile. And 90th percentile. Now I'm going to do the same thing down here for process 2. So this is 10th percentile. That's going to be equals risk percentile for this guy right here. And 10th percentile. And I'm going to multiply it by 500 as well. So it's $500 per robot. And you can see I get a different value down here because we have a different distribution for our times. I'm going to copy and paste that and change it to the 50th and 90th percentile respectively. And you can see right here that our expected value is less if we go with automation. We get 65,917.5 versus 71,084. So we should decide not to go without automation and stick with the status quo. Last example, we use the extended Swanson-McGill method for creating our decision tree. We're going to change that over to being the extended Pearson-Tukey scale and see if anything changes. So I can do this with the extended Pearson-Tukey scale as well, but some of the values change. So I'm just going to modify my tree accordingly. So instead of looking at the 10th and 90th percentile, these are now going to be the 5th percentile and 95th percentile. I'll change it down here as well. So I just changed the names, but let's actually change the values now. So I'm going to change this from the 10th percentile to the 5th percentile. We're going to change this to the 95th percentile. Same with down here. And I'm going to change the percentages. So this will, using the extended Pearson-Tukey scale, this should be 18.5, 63, 18.5, and again 18.5, 63, 18.5. And again, it doesn't really change the final outcome. We're being told to stick with the status quo and do not automate.